We are going to examine fluid dynamics now, which is what happens when fluids are moving instead of staying still. We are going to assume again that the fluid is incompressible, meaning that volume and mass is conserved when it's moving, and that the density of a fluid stays the same throughout. And so since volume doesn't change and density doesn't change, the mass also doesn't change. So now let's consider um, a tube that's guiding a fluid that changes in diameter or radius. So we have a tube that starts off small and then gets bigger. Now we know that the area here, A1, and then area 2, A1 is less than area 2. But then we know that volume here, volume is equal to area times this distance that we're having. So this is the length of this like cylinder of fluid. So we can call this change in x1 and then change in x2. Now, since volume is conserved, we know that since volume 1 has to equal volume 2, since the fluid is compressible, as in any volume we put into this side has to come out this side in the exact same amount. We know that area 1 times change in x1, or the distance 1, is equal to area 2 times change in x2. And this is the continuity equation. Well, this is a continuity equation. We also know that this change in volume has to occur over the same period of time, as in if we put this volume in this side through a certain time interval, let's call it change in time, then we know that the volume over here has to change by that same amount in that same time interval. And now, if we look here, this is just velocity, change in position over time. So we can rewrite this as area 1 times velocity of the fluid at the point 1 is equal to the area of this tube at point 2 times the velocity at point 2. And so this is also a continuity equation. And so area here is inversely proportional to velocity, as we can see here. So as area increases in a tube or in a path for a fluid, the velocity has to decrease, and and vice versa. Okay, so this is important to remember. And now this area times velocity here has units of cubic meters per second, and this is the flow rate for a certain fluid inside a tube. So this is how much fluid is passing through this tube per unit time. Now another important equation that we can derive is Bernoulli's equation, which comes from the conservation of energy. So now let's consider we have a tube with moving fluid that changes in both elevation and size. And we want to know what happens to the velocity of the fluid and the pressure of the fluid. So we want to examine the same amount of, we want to examine one amount of mass and see what happens to that amount of mass. So let's just say we take this column of fluid here, and it has a set mass. And then at this side, since we saw here, the volume has to be conserved, which means mass has to be conserved since the fluid is incompressible. It will occupy something like this volume of space. Now, since these both have the same mass and the same volume, let's call this here area 1, and then this area 2. Call this distance here change in x1 and change in x2. We know that change in x1 has to be greater than change in x2 since area 1 is less than area 2. And then let's call this height here. This section of the tube has height h1, and then this has a greater height. So this is a change in height. But then this section of the tube here has height h2. Now, from conservation of energy and the work energy theorem, we know that change in energy is equal to work. First, let's look at where work comes from. Work is equal to force times distance, and force is equal to pressure times area. So work here is equal to pressure times area times distance. And now this distance term is just the change in x that we identified. So let's look at the work being done on the system and the work going out of the system. So we have the work on side 1. Work on side 1 is equal to the pressure at side 1 times area of side 1 times change in x1. And now we can write this as just the volume of water here. And we know that the volume, since the mass is the same and the fluid is incompressible, meaning the density is the same, the volume is also the same. So we have work 1 is equal to pressure 1 times volume. And now the work on this side here, so work 2 is equal to pressure on the output side times area of the output side times the change in x of the output side. Now, this again we can write as volume. Since volume is conserved by a continuity equation, we know that these two are the same volume. So we write work 2 is equal to pressure 2 times the volume. So pressure 2 here times the volume. And now the net work, so the total work done is going to be equal to the difference in this, because work 1 is the pressure we're putting into the system, and work 2 is the pressure is the work we're doing out of the system. So the total work is going to be equal to work 1 minus work 2, which is equal to volume times P1 minus P2. And we know that this is equal to the change in energy. Now, what types of energy are there? We have kinetic energy, which is equal to 1/2 mv squared, and then potential energy, which is equal to mgh. Now, for fluids, we usually don't have a definite mass. We just have density of a fluid. So we want to put all these in terms of density. And we know that mass is equal to density times volume. So we can write this as kinetic energy is equal to 1/2 density volume times velocity squared. And then potential energy is equal to density times volume times gravitational field strength times the height. Now the density, again, these are the same densities since the fluid is incompressible, and then again these are the same volumes as before too, since the fluid is incompressible. So we know that the change in kinetic energy here is going to be equal to 1/2 rho, since the density doesn't change, since the volume doesn't change. So it's just V1, or the change is the final minus initial. So it's V2 squared. So V2 squared minus V1 squared. And now change in potential energy is equal to, again, density doesn't change and volume doesn't change. Gravitational field strength also doesn't change. So it's just equal to the final height squared minus initial height squared, or not squared, just the final height minus the initial height. So now if we combine these, we get that the work, which is volume times pressure 1 minus pressure 2, is equal to the change in kinetic energy. So that change in energy equals change in kinetic energy plus change in potential energy. So the work is equal to the change in energy, which is equal to 1/2 rho V, V2 squared minus V1 squared and then plus rho Vg H2 minus H1. And so we see that V here appears with all the terms, so we can cancel it out. And again, this volume is the same for all these V's are the same because the volume is conserved for incompressible fluids, as we saw before in these two examples. So we get that P1 minus P2, so these are the pressure differences, is equal to 1/2 rho V2 squared minus 1/2 rho V1 squared plus rho GH2, so rho GH2 minus rho GH1. And rearranging the terms here, we get that pressure 1 plus 1/2 rho velocity 1. Let me rewrite this to make more. 1/2 rho V1 squared plus rho GH1 is equal to pressure 2 plus 1/2 rho V2 squared plus rho GH2. So this is Bernoulli's equation, and this is probably the singular most important equation in fluid dynamics. And it describes conservation of energy. So this term is related to the work done. This term is related to kinetic energy, and this term is related to gravitational potential energy. Now, another way we can write this is pressure plus the kinetic energy. So pressure plus 1/2 rho V squared plus rho GH equals a constant value, since V1 and H1 and V2 and H2 can be any 2 points arbitrarily picked in the liquid or in the fluid. So that means that fluid, this sum has to be constant for all places in the fluid. And again, that's conservation of energy. Now, one place where this can be easily applied is when you have a setup that looks like this. So let's just say you have a large tube that drops down to a small tube, and then you have another tube that goes like that. So let me redraw this line. So something that looks like this. If you have a fluid moving through here, we know that, first of all, we know that the velocity here, and then velocity 1. So we know that velocity 2 is greater than velocity 1, since the area at point 1 is greater than the area at point 2, and this comes from our continuity equation. And then now, since we can consider these at the same height, we know that from Bernoulli's equation, if pressure 1 plus same height, so the gravitational potential energy terms get canceled out. Pressure 1 plus 1/2 rho V1 squared is equal to pressure 2 plus 1/2 rho V2 squared. We know that since velocity is greater, that means that this term here is greater than this term, which means that if this term increases, then this term here has to decrease in order for this to remain constant. So we know that as velocity increases, pressure has to decrease. So now, looking back at this apparatus, let's say we have another fluid here. Now this fluid is static, so this yellow fluid is not moving. But notice that it's at a different height, so there's a change in height here. And this is because there's lower pressure here, higher pressure here. So the fluid has to be at different levels. Because here the pressure is the same, but then there's low pressure on here, high pressure here. So that means that this section of fluid that's raised up has to provide the extra hydrostatic pressure to help create that, or to sustain that pressure difference. So we can calculate this. We can calculate this change in height by finding first the pressure at this point, and then the pressure at this point, and then applying that difference in pressure to the hydrostatic pressure equation here. So let's do that right now. So we have pressure 1. Really, we want to find the difference in pressure. So pressure 1, or we can do pressure 2 minus pressure 1 here. Pressure 2 minus pressure 1 is equal to, so 1/2 rho V1 squared minus V2 squared. All right, so this is the difference in pressure. Now, we can call pressure 1 P0. So we know from the hydrostatic pressure equation, we know P is equal to P0 plus rho GH, right? Let's call P pressure 2 and P0 pressure 1. We can rearrange this to get P minus P0 equals pressure 2 minus pressure 1 is equal to rho GH. And so this is, that way we don't actually have to solve for pressure 2 and pressure 1. We just need to solve for the difference. So the difference of this is, let's call this fluid 1 here, and then this is fluid 2. So the difference in pressure is going to be 1/2 rho 2 minus v times the difference in the square of the velocities. And now the hydrostatic pressure is equal to the difference in the pressures, or the difference in hydrostatic pressure is equal to density of, this should be density of the first fluid. So the difference in pressure caused by the different velocities is related to the density of the first fluid here. But then the hydrostatic pressure from this bottom fluid is related to the density of the bottom fluid times this height and the gravitational field strength. So setting these equal, we get 1/2 1/2 rho 1. So this is the density of the moving fluid times the difference in the squares of the velocities is equal to rho 2 times g times h. And so solving this, we get h is equal to rho 1 times v1 squared minus v2 squared over 2 times rho 2 times g. And now notice we set this here as pressure 0 and this as our final pressure. But notice that this is actually lower, which means this has higher pressure than that. So our H will turn out negative because we set this as our initial pressure and this as the hydrostatic pressure. So if we want to find the positive value of H, we just get, so the absolute value of H is going to be equal to, since we know that V2 is greater than V1, we know that the positive value of H is just going to be rho 1 times V2 squared minus V1 squared over 2 rho 2g. And so when we have something that's moving slower going to something moving faster, there's lower pressure at the part that's moving faster, which means that there will be a height difference in this liquid if we have this setup. Now, another special case we can consider is how related to how siphons work. and that's Torricelli's case, where we have a large container of water here, or liquid, and a small opening, so that this water level here, this is filled with liquid, and then there's a stream that pours out. Now we want to know what the velocity of the water coming out of this stream is. So we know that this area here, and then this area here, area 2 is the area of the hole. Area 1 is much greater than the area of the hole, which means that since it is much greater, we know that velocity 1 is going to be pretty much 0, because as we saw before by continuity, if the area is much greater, then the velocity has to be much, much less. So we assume that this area is great enough to where this velocity at the top here, v1, is basically 0. So we can consider this top of the surface not moving. Now, this has a distance h, or a height h below the surface, this hole. So now if we do Bernoulli's equation, we know that the pressure 1, which is atmospheric pressure, because this is open to the atmosphere. So atmospheric pressure plus 0, because we know that our velocity is basically 0. So we can cancel out the kinetic energy term plus rho gh, so this is the potential energy at that point, is equal to, since this hole is also exposed to the atmosphere, this has atmospheric pressure. So atmospheric pressure plus 1/2 rho v squared plus 0, because we're setting this as our 0 for the height. So solving this for v gives, first we can cancel out the atmospheric pressures, and then doing algebra to solve for v, we get that v, the velocity of the stream, is equal to, we can cancel out the densities too, because the density stays the same on both sides. So this velocity of the output is going to be equal to the square root of 2gh. Notice how it only depends on the height. It doesn't depend on the area of the stream, as long as this area of the output is much less than the area of this total reservoir. And so the velocity is proportional to the square root of the height underneath the surface, which means that if you have some outlet here, if you have an outlet that's much higher than an outlet down here, we see that this outlet falls like that when this is filled with water, whereas this outlet falls like further, well, this outlet goes further because it has greater velocity. So the velocity, exit velocity of the stream is proportional to the square root of the height of this outlet underneath the surface of the water. And this relates to siphons, because when you have a siphon, the outlet is lower than the surface of the water, which means that there has to be a positive velocity that's going out the other end of the siphon, which means that water has to be exiting from the siphon. And so that is why water goes out of the siphon.